Now that we've discussed the training strategies that you can use for the individual learners, here we discussed bagging and boosting. Now it's time for us to see how we'll combine the predictions of the individual learners. At this point, we have multiple models trained on our dataset. Either they've been trained in parallel on different random samples of the input data, or they've been trained in a sequence where each model learns from the mistakes that the previous models have made. Once we have these trained models in an ensemble, let's say a new prediction instance comes in. Every individual model in the ensemble will output its own prediction on this new instance. The prediction will be a continuous value for a regression model and, of course, a class or a label for a classification model. Now, if you have a classification model, one way to aggregate learners is by voting. It's a simple yet powerful ensemble strategy. Each base model independently predicts a class, and the ensemble selects whichever class gets the most votes. If you just count the majority votes, that's hard voting. And if you average the predicted probabilities for each class or label, that's soft voting. I'll discuss that in more detail. Averaging is the go to method for regression ensembles. Each model makes a numerical prediction, and the final output is simply the average of all those predictions. This reduces variance by smoothing out the individual model errors, kind of like pooling multiple forecasts to cancel out noise. If the models are reasonably diverse and unbiased, the average result is often more reliable than any single prediction in isolation. Averaging is pretty straightforward, but voting needs a little additional explanation. There are two types of voting. With hard voting, each base model independently predicts a class label, and the ensemble chooses whichever class receives the most votes. A simple majority decides the outcome. So, if out of 100 models, 70 predict class A and 30 predict class B, the output of the final ensemble will be class A. It's a straightforward method where consensus across models drives the final decision. It's reliable, but it ignores how confident each model is. It treats all votes as equal. Soft voting takes model confidence into account by averaging the predicted class probabilities from each base model and then selecting that class with the highest average score. This method can be more accurate where the models output well calibrated probabilities, as it weighs stronger signals more heavily. This confidence weighted approach often outperforms majority voting in nuanced scenarios. In addition to averaging and voting, there is yet another third approach that you can use to combine model predictions, and that is stacking. This uses a two-layer approach. First, multiple base models make their predictions independently. Then, a meta model or a blender or a combiner is trained to take those predictions as input and produce the final output. This meta learner learns how to best combine the strengths of different models, and it often leads to higher performance than any single base model. Here is a visualization of what a stacking ensemble looks like. Once again, we have multiple models in the ensemble trained on the input data. This could be bagging techniques, pasting techniques, or boosting techniques. It doesn't really matter. Rather than just combining the predictions of these models using averaging or voting, you train a new meta model or a blender to predict the final output. The meta model is the higher level learner that takes the predictions from the base models as input features and learns how to best combine them to make the final output. For instance, it might learn when one base model is overconfident or wrong, another can correct it. Essentially, learning weights or patterns amongst base model outputs to boost overall performance. Often, this meta learner is a simple algorithm like logistic regression for classification or linear regression for regression tasks.